Our next suite of functions, our inverse trig functions. Now let's see how we differentiate those. First of all, let's start with inverse sine x. Well, we know how to differentiate the sine function, so let's rearrange it. X equals sine y. So instead of finding dy dx, I'll find dx to y. When we differentiate sine, we get cosine. That's dx to y. Turn it upside down, I have dy dx. But alright, it's in terms of y, not in terms of x, which is okay. But let's get x back in there. How can I? Well, I can rewrite the cosine of y, and through a few steps I get there. Cosine y is the square root of cos squared. Cos squared I know is 1 minus sine squared, and we said sine was x. I get my answer. 1 on the square root of 1 minus x squared becomes the derivative. Let's do a similar thing for inverse cos. I'll make it x equals cos y. Cos goes to minus sine. Turn it upside down. Now, how do I get the x in there? I'll do the same sort of thing. Sine is the square root of sine squared. Sine squared is 1 minus cos squared. We get two very similar integrals. It's just that one is positive and one is negative. The inverse cos 1 goes to negative 1 on the square root of 1 minus x squared. Inverse tan. X equals tan y. Tan goes to sec squared. So dy dx is 1 on sec squared. I don't need to do the square root of squared because I've already got the squared. But sec squared is 1 plus tan squared, so we get 1 on 1 plus x squared. So there's the three main inverse trigs. So let's look at that to generalise it out. If it is a linear function, x over a though, I've written it as rather than a times x. X over a, then it becomes 1 on the square root of a squared minus x squared. Inverse cos, the same thing, but it'll be negative. And this is where we need to be careful, because inverse tan doesn't have 1 on the top. It actually has a on the top. So you get a on a squared plus x squared. That's why you might find it easier just to remember the one for any function, because that pattern is similar through all three. Inverse sine, it's inverse sine of a function. So you differentiate the function that goes on the top of the fraction over the square root of 1 minus that function squared. Inverse cos is the same but negative. And then inverse tan, differentiate the function, that goes on top, and then you got 1 plus the function squared. So I personally prefer that because the pattern's the same in all, the derivative's the same on all of them. So let's have a look at an example. So inverse sine of 5x. Alright, it is a simple linear function. So I could have put it in the other one, but hey, using this derivative idea, look what I can do. I can say, well, hang on, the derivative of 5x is 5, that goes on top, over the square root of 1 minus the function squared, 25x squared. Inverse cos of e to the power of x, okay, derivative of e to the x is e to the x. This one's negative though, so you get negative e to the x over the square root of 1 minus the function squared, e to the 2x. Inverse sine of x on 3. Alright, that's the one where the x on a one becomes really good, because I can just go straight into the answer. 1 over the square root of a squared, which in this case is 9 minus x squared. If I had used the other one, I still could. I'd go, well, the derivative is a third, so a third goes on the top, over the square root of 1 minus x squared on 9. Well, we don't like fractions on fractions, so I'll multiply everything by 3. I've just pulled the third out here just to highlight that, yeah, even though that's over 9, it's actually over the square root of 9, so it is also over 3. So you end up with 1 over the square root of 9 minus x squared. E to the power of the inverse cos x. So it's an exponential function we're differentiating. And we said, well, how do we do that? We differentiate the power, it goes out the front, e to the, and then the power doesn't change. Well, the power in this case is now inverse cos. So differentiate inverse cos, and I get minus 1 on the square root of 1 minus x squared. It'll be that times e to the, and the power doesn't change. I just might write that all as one fraction, a little bit neater, but there's my answer. Okay, chain rule, anarchy. Bring down the power, 3. Lower the power, 2. Diff the inside. Well, inside I've got inverse tan x. Differentiate inverse tan x, I get 1 on 1 plus x squared. Let's tidy all that up. Here's my answer. And remember, with inverse trig, we don't write this inverse tan squared as to the power of -2 because that -1 does not mean that the power is -1. It's symbolizing the inverse function. So we write it as inverse tan x, all of that squared. Ooh, product rule. Write down the first, x squared. Diff the second. Well, the second bit is the inverse tan of x cubed. So I differentiate the angle, 3x squared, over 1 plus the function squared. The function is x cubed, square that, I get x to the power of 6. Plus, write down the second, inverse tan of x cubed, differentiate the first, differentiate x squared, we get 2x. Let's tidy all this up. I guess I could factorise out the x as well, but I'll just leave it like that. It doesn't really get much more. So. Alright, let's have a look at some HSC questions. We've been told our function is the inverse sine of x plus the inverse cos of x. Okay, that's what we've been told. We have to show that the derivative of this is equal to 0. Okay, well I'll differentiate. Differentiate inverse sine, I get 1 on the square root of 1 minus x squared. Differentiate inverse cos, we get the same thing but negative. So yeah, they're going to add together to give 0. Nice little gift mark to start off with. But then they say, hence or otherwise, prove that actually these two things equal pi on 2. Now the idea they're getting at here, if the derivative is equal to 0, then the original function must have been a constant. Because when you differentiate a constant, you get 0. So therefore, we know function x is a constant. Oh, and also we know they're continuous functions as well, so we don't have an issue there. Well, if I know it's a constant, all I've got to do is substitute a number into that function, and I can work out what that constant is. So substitute in 0, I get 0 plus pi on 2, which is pi on 2. There's my constant. We have that inverse sine of x plus inverse cos of x is equal to pi on 2. But here's the bit that got people. Hence sketch function x is the inverse sine of x plus inverse cos of x. And what a lot of people did is they simply drew the horizontal line y equals pi on 2 because we just said it was a constant. But we are substituting into inverse sine of x and inverse cos of x. They have restricted domains. So the actual graph is just the piece of that line going between -1 and 1. Because we can't substitute in numbers outside that domain. So it's just that piece of the horizontal line. Let's look at this one. It's a similar sort of question, but to show you the difference between the two here, because there's different issues happening. So now the function is the inverse tan of x plus the inverse tan of 1 on x. So we'll start it off the same. Show that the derivative is equal to 0. Okay. Same idea, let's differentiate both of them. The first one's 1 on 1 plus x squared. The second one will be, well, differentiate the function, which is 1 on x, differentiate that, we get minus 1 on x squared, over 1 plus that function squared. Fractions on fractions, multiply top and bottom by x squared. And again, we got the same thing, but one's the negative of the other. So yes, it does equal 0. Sketch it. But this time we have a discontinuous function at x equals 0 because we're going to be substituting into 1 on x. I know x can't equal 0, so because it's not a continuous function over its domain, this brings up an interesting issue. I need to pick a number to work out what that constant value is going to be, like I did with the last one. I can't use 0 this time because it's discontinuous there, so I'll pick 1. And similar to the last question, I get pi on 2. But look what happens when I pick a point on the other side of that discontinuity. If you substitute in -1, you actually get negative pi on 2. So in a question like this, when there is a discontinuity, you need to pick a point either side of that discontinuity because the constant value might not be the same on either side. So when you draw this one, on the right hand side, and the domain for inverse tan, remember, is normally all real x. So it doesn't stop. This one does keep going. And then on the left-hand side, we get the negative pi on 2. Let's now look at the 2020 paper. This one was quite good. Suppose our function is the tan of the inverse cos of x. That's one function. And we have this other function, the square root of 1 minus x squared over x. And they gave us a graph of the second one. There's y equals gx. Show that these two functions have the same derivative. Okay, well, let's differentiate them. The first one, the tan of the inverse cos. So I'm differentiating a tan function. What do? We differentiate the actual function, and then tan goes to sec squared, the angle doesn't change. So I have derivative of inverse cos of x is minus 1 on the square root of 1 minus x squared. Tan goes to sec squared, the angle doesn't change. How on earth is that other one going to all of a sudden have trig in it? Well, it doesn't, because I can keep going with this one. Sec squared, well, sec is the reciprocal of cos. So on the bottom now I have the cos of the inverse cos squared. Well, cos and inverse cos, they're inverses, so they cancel each other out. That becomes x squared. So I have minus 1 on x squared root 1 minus x squared. Now let's differentiate the other one. Got to use a quotient rule. Square the bottom. Write down the bottom, x, diff the top. Well, the top is the square root of 1 minus x squared, which is 1 minus x squared to the power of a half. Bring down the power, a half. Lower the power, minus a half. Diff the inside, we'll get negative 2x. And so eventually we'll get minus x on the square root of 1 minus x squared. Minus, write down the top, square root of 1 minus x squared. Diff the bottom, differentiate x, we get 1. Let's tidy all that up. Well, again, I've got this fraction on fraction issue. So I'm going to push the square root of 1 minus x squared to the bottom of the fraction, but that means this second term is now multiplied by the square root of 1 minus x squared. So we end up with minus x squared, and then the other bit becomes minus 1 plus x squared. We get the same answer. That was part 1 of this question. But I suppose, all right, if we couldn't prove it, at least we've got this fact now we can go and use in the next parts. And it gives us that big hit. Hey, we just got you to do that because you're going to use part 1 in this, if you're sensible. It does say or otherwise if you want to go a different way. Show that the actual functions are the same. So even though we've drawn a graph of gx, that would produce the same graph for function x. We're going to prove they are the same thing. Well, we've shown in part I that their derivatives are equal, so that's a good starting point. I'll move everything to one side. What I'm saying is that the derivative of the function we've labelled f minus the derivative of the function we've labelled g, that's going to equal 0. Because once I've got it to 0, I can use that constant idea like we did in those other examples. I know the derivative is equal to 0, therefore when I integrate it, I get a constant. So I know this is a constant. So whatever function x is, when I integrate the derivative, I'm going to get that function minus whatever the function is, differentiated, I'll get gx. I know that that is equal to the constant. So function x does equal g of x plus some constant. Hopefully that constant is 0, because if it's 0, then we can say they're equal. When x is greater than 0, sub it in, I get function 1 minus g of 1. Subbing that into our function, I get the tan of the inverse cos of 1 equals the square root of 1 minus 1 squared over 1 plus a constant. So I've moved the g back on the other side. So like here, function x equals g of x plus a constant. That's what I'm substituting in. Constant equals 0. But what happens when it's negative? What happens when it's negative? Is that 0 as well? So sub in, yes, that is 0 as well, indeed. Why did I check either side? Let's go back to what those original functions were. So remember, we have a discontinuity at x equals 0. So I need to test either side of that discontinuity, and it was good. They did both turn into 0. Thus, we know these two functions are the same thing. So 12a, now we can differentiate our inverse trig function.